What's below the computer or tied to the computer is a physics or a chemical or mechanical or other system. Okay, that's one. And the other is you have tremendously powerful computer languages and tools right now, which I will describe. So the first challenge from a project we have with Vanderbilt University from the Institute for Software Integrated Systems that's headed by Dr. Stepanovic, who is a collaborator of mine. We have problems like this. You're trying to design systems that they have this kind of pieces, which is behind, for instance, the META program of DARPA, or the adaptive vehicle of DARPA, right? This is or the IFAB of DARPA. Okay, so this all has reached that point where they go into programs of that national significance. In a system like this, you may have electrical domains, mechanical domains, hydraulic domains, thermal domains. And the significance of systems engineering is that the logics, the rules of the designs that you need to capture to be able to understand requirements and do your trade-offs are different in each one of these domains. Okay? None of these domains is as like as electrical, where you have Maxwell's rules, and many of the rules come out of there. There you have much more complicated things. And then if you look at the theoretical side of things, or the analytical or the language side of things, you have plant dynamics. They need models. You have controllers. They need models. You have software architectures. They need models. All of these need models, each with different logic, and then you have to integrate them. So you have to integrate the software side and the algorithms. You have to integrate the physical side, then you have to integrate the two. Okay? So what everybody understands today, which they didn't understand 20 years ago, is that nobody's going to do it all. We used to go to companies pre-INCOSE, and nobody's going to open their kimonos to tell you about system engineering because they thought it was their discriminating strategic knowledge. Well, that's gone. Everybody understands. I'm not going to name any company because some people may be here, or institute. What we are looking for is a framework to integrate a variety of tools of different kinds so that anybody who wants to do quantitative systems engineering can do it. And that's what I'm going to describe, that we're working in Maryland now for about 10 years. And we finally, and we're not the only ones, there are other people, but I'm happy to see how many people are getting into these kind of things today. So what we teach in Maryland, this is a slide that we have been using for almost 10 years. And as I said, the slide is easy. The devil is in the details, right? Because we all understand this slide once I explain it. The difficulty is how and what tools you use to do this. So let's go through it anyway. This slide actually is inspired by work we were doing with Oliver from General Electric when he published this book of complex systems, for those of you who are old enough to remember. So you collect the requirements and the information about the system. And then the first idea that became clear was you have to answer two questions. What the system consists of, meaning the structure of the system, and what the system does, which is the behavior of the system. And in many disciplines, they do one or the other, and they don't do both. Okay? And then you have to allocate pieces of structure, of behavior to structure. So I want to understand the braking of a car. Which components are going to be involved? The brakes, the shock absorber, the seat, the wheel, what? Right? It's not anymore just the brake involved. As a matter of fact, for many of the modern cars, when you press the pedal, you don't do anything mechanical. This is just a switch that starts the electronic braking. Okay? That's why you had problems in Toyota. So you do that, and you have to do that in a hierarchical way, and you keep doing that until you find something that seems to be reasonable. And then at that point, you are ready to translate some of the requirements that are typically written in text to mathematical expressions that typically include constraints. And the constraints you represent as inequalities or logical rules or metrics. Unfortunately, in many of the systems of today, the variables that are involved in these constraints and rules, they include both logical variables, meaning Boolean, and numerical. And that's a big difficulty because there are not many schools or many engineering schools or whatever discipline that they train people to work in both what I call calculus-based quantitative thinking and logic-based quantitative thinking. The term we use now in systems is in the part of systems that does, if you like, analytics and theory and algorithms, it's called hybrid systems. Hybrid captures the logic via the Boolean and the physics from differential equations, the numerical variables here. And you need both. An airplane or a car has the physics, but it also has tons of computers on it. Okay. So, and you need for all of those models. And once you do that, and you have translated the requirements to what I call specifications, just to make a distinction. A specification is something that has a mathematical expression. You're ready to do trade-off analysis. And trade-off analysis, usually, it will involve multi-criteria optimization or constraint-based reasoning to capture both the logic and the analytic part. And I'll tell you what we're doing in that area. Every time you go through these loops that you see here, you may you may split a component, or you may create new components, and so on and so forth. When you are done, not only you have this, but you also have what I will call an architecture, because you have a structure, the wheels, the doors, whatever, and then you have a behavior, which means the car stops, cruises, brakes, okay, or various things that they are the dynamics of, if you like. And then in the last, you have to actually do the test and validation. So point number one, forget the V diagram, at least the simple V diagram. That doesn't work. The modern theory is that at least if you take the V diagram, and most of you know, you have to include lines at this point, okay, to be able to do checking and adaptation at different levels and at different parts of this block diagram. Now, we have been teaching this in Maryland since 2000 in 3 courses that we developed with support from NSF in our core Master System Engineering program. And the tools are not easy. So let me go through some of them so that you understand the difficulty of teaching this subject and why you need teams and why nobody's going to do it alone. So you all know UML SysML. You all know the problem that SysML has because it doesn't have correct semantics, and people are trying to correct that. But it's a useful language, and I'll tell you how we're using it. GME is something that is being developed at Vanderbilt, which is a bond graph type of methodology to create block diagrams that they have semantics. Without semantics, you are in trouble. Because what you want to do is you want to be able to have these diagrams, push the button, automatically execute code, and correctly have simulations. Otherwise, we want to be here for centuries trying to do a complex system. Imoflon is one that I will use, which is equivalent to GME. It's a framework with rich semantics that allows you to build meta models, models of models. Because one of the things that we now realize is that we need to be able to transform models from one domain to the other in a more, if you like, colloquial English. You have to allow the various engineers to wear their glasses. If I'm a mechanical engineer or electrical engineer or chemical engineer, look at what the framework that you have gives me, understand what I have to do from my own perspective, and leave something behind for the rest of the people to understand in terms that they can understand. And that can only be done by introducing meta models and these transformations in a way that is semantically correct. Right? Because, again, nobody's going to learn all that. You're going to learn a piece of it, and then hopefully some people will have created a framework that allows these tools to interoperate. Then you all know the IBM Rhapsody tool. We're working with them. There are big holes in what they have, and they know them, and we're working with them, and I'll describe them. UPAL is a formal modeling tool that is open. It comes from Sweden, and it allows you to write formal specifications and rules and check them. So when we try to do model validation now, one thing that we try to use more and more is ideas from model checking from software, but now it becomes more difficult because we want to do similar things for mechanical systems, for electrical systems. And what's the difficulty? Well, the answers are not yes or no only, and they're not Boolean variables. How do you specify that the trajectory of a missile or a trajectory of a robot is going to stay within the bounds of a trajectory in a tube in 3-dimensional space? And you have to be able to test and verify that. That's a much harder problem than writing down a rule and a logical expression and tell me whether it's true or false, which is what you do in model checking. So in these hybrid systems, to try to be able to do checking and validation, it's much harder. We're making progress, but we have a long way to go. Then you all know doors. I was working with TI when George Harmayer was at TI, and he was in our advisory council here at the Institute. And I knew the group that created doors. And all I'm going to say is, let's not talk about it right now. We'll talk about it later. In the US, we have a major problem because we have nothing like the ARTIST consortium in Europe, which are working on these things systematically with the best academics and industry. And we have been pushing the various agencies to create something like that. We'll see. We're using Modelica Dimola because it's a much more sophisticated thing than MATLAB, especially if you want to have multi-physics models. And Dimola, of course, is part of Dassault system. And if you ask me, currently, in this kind of language and in this kind of sophistication, the company that has the best tools integrated is Dassault Systems, and that's why both Boeing and the Europeans, when they build complicated aircraft, they use their tools. But it cannot remain that way, because we have to open it up. We have to create an open environment where people can contribute to various tools. We have to get away from this, oh, now this is my tool, it's not going to play with yours, and I'm going to have it all, because I am XYZ company, and I'm a better system integration company than his company, and this company, and so on and so forth. That is in the past, but it still exists somewhere. Now, Cplex is a multi-criteria optimizer, which was created by a group at Houston. It was bought by IBM. eLog was a company that has the best rule solver in the world. It started a startup from Iria, from France. They moved to Silicon Valley. They became private. It was bought by IBM. There's a reason why I'm telling you that. And these two work together. So industry went ahead of the academics, and they showed how they can combine constraint-based reasoning, which is this, with optimizer to do very complicated rules. The interest of IBM's, when they bought these companies and to do it, was primarily to create powerful tools for enterprise management and software, not so much engineering. Now, because of various groups that they have started interacting, they're interested in engineering. Okay, again, I have to say that whatever names I give for software, I'm not advocating to use those. Think of them as examples or as instances of the type of software we have to include in the environment I'm about to describe to you. Okay. This you all know that you have to do this diagram of the previous thing in a hierarchy, and you have to go from gross to fine and back. And the difficulty for that is that if you're going to describe rules and constraints, you have to understand how you're going to do aggregation, disaggregation, so that they become consistent. If you lose the semantic correctness at any point, you lost the game. And that's very difficult to do, because not everything is going to decompose neatly, okay, in subsets of rules with a neat interface. Okay. So as far as SysML, you all know why it was created, because UML primarily came from software, and it was not very good to describe block diagrams like we need in engineering. And the new things that came with SysML was the requirements diagram and the parametric diagram, which we use actually in some of the things I will describe. Okay? And we use we link the trade-off tools that I'm about to describe here, okay, and in the requirements diagrams, and they manipulate these two diagrams that you have. Okay? The rest is more or less the same as it was using UML. And it's good that UML and SysML, they overlap, because you get the state charts from UML and other things you need, which have reasonably good semantics, but SysML has to strengthen its semantics a lot. All right, so you have structure in SysML, structure diagrams, behavior diagrams, okay, and you have parametrics and requirements. You are members of Encosi. You know this is textbook for Encosi at this point. Okay, so how we use SysML is where we, I think, innovate a little bit. And whenever you innovate, you also get criticized. That's okay. We'll see what you say. So we use SysML as a block diagram language. Because of its weak semantics and so on and so forth, we cannot really do much more than that. But this is extremely useful because we anchor with these various tools. So we start from requirements, and then we create the architecture model like I described by playing behavior and structure and mapping behavior into structure. And we do this represented in SysML. And then now we can interact with various tools. So if you like optimization, you can have Cplex, or your own optimization. If you like dynamical systems, you can use MATLAB or Simulink or Dimola or COMSOL, whatever is your choice. And then if you have hardware in the components, you can link to hardware at the different levels of hierarchy you have. And you have software, you do the same. You can use finite state machines, describe the software, and so on and so forth. Okay? And you can have verification models. So the point is, the arrows is the key point. They have to interoperate. If I take one out and put another one, they should be able to operate. Again, I emphasize, I describe a framework, not a particular set of tools. Right? And in this is going to be important to be able to translate, okay, various models. So if I use Dimola and you use MATLAB, or somebody uses a mechanical modeler, we have to be able to transform the one model to the other for the variables that matter for the design. Okay. And for that, we need to have model transformation tools. Some sort of meta-modeling is necessary. And I'll show you how complicated this can come. And then these are various tools for modeling and various domains, and you have domain-specific languages that you can do that for. And then through the meta model, you communicate. To do that, using SysML, you have to use profiles. If you are involved with the OMG, you know that there are people that they try to create profile sets so that they can create these links, and we already have a good one with Modelica. There is one informal one with MATLAB, and there are many more working on. Okay? So these profiles allow you to link to SysML and then to any meta modeling environment you have, and then be able to do these transformations and carry the parameters and the constraints and the parameters that you will need for design exploration. So our vision is on this slide. If you don't get anything away from this talk, at least get this. All right? And then we can discuss it. I'm not preaching here. I'm just proposing things. All right? And I'll show you what we have done. This you already saw. You saw this. There are two more important pieces. You have to link this to trade-off analysis tools. You need to be able to go here and do design exploration seriously, not I have this design, I changed this parameter a little bit, that's my new system. You have to really do design space exploration, and be able to do that, you have to have serious industrial strength, multi-criteria or constraint-based reasoning tools to argue with the various parameters you have here and be able to do design exploration. And that is a tremendously complex exercise. And I'll show you what we have done in terms of a divide and conquer to be able to make this into pieces and be able to try to conquer it. The other thing you need, and this is very difficult, many of the companies that are here and we work with, they are not going to do a system design from scratch. They have previous designs for 50 years. And they have somewhere stored the plans and other things. So let's call these stored plans and designs a database of all designs. So what you need is you need a way to reverse engineer the software you have and search them and see if any of the things you need here you already have in some form or another. Not trivial. Just remind you how difficult this was when people went from COBOL to other types of programs 30 years ago in the business world. Okay? This is a hard problem, and companies like IBM and others, they are devoting personnel to try to develop this kind of products. I want to develop a sensor network. I am looking for sensors, okay? I am in the sensor business. Maybe I have a sensor that I designed 10 years ago, 5 years ago, which at least in the way that I describe it is close to what I need. I don't need to start from scratch. So you need this, and you need this, in addition to the modeling. So what are the problems if you're in trying to make systems engineering rigorous or quantitative? 3. You need what we call, and I'll describe what we have done, an integrated modeling hub. You need to be able to model heterogeneous systems at different hierarchies so that the models can communicate. You need an integrated modeling hub, and this is what it's trying to capture here. You need to link that hub to a trade-off set of tools to be able to do design space exploration. I'll discuss that. And then you need the most difficult problem of all, to be able to take requirements from language, translate them into something that is mathematizable, and put them into here. I will discuss very little about that because we haven't done much in this area, and it's the most difficult problem. And I can tell you now, it's not going to be solved by doors. Okay? We need a lot more sophistication to put here than doors. But you can start from doors, and I'll tell you what's happening right now in this domain. So now I'm going to preface some of these developments by real applications. Okay, so this is the Dreamer aircraft, right? Why was the Dreamer from Boeing? Because it's the first aircraft that has composite wings. And why this is a beautiful system engineering problem, there are many, is because it's an all-electric aircraft. I mean, this is the era, some people say, of the all-electric platforms, all-electric cars, all-electric homes, all-electric vehicles, all-electric aircraft. Why? Because there's a thought that electricity is the more efficient and more controllable form of energy. But let's not go there. There are many interesting system engineering problems here that Boeing did, beautiful work, to relate the properties of the composite wing. That's when they proposed it, everybody thought they were crazy to do a composite wing aircraft, with the abilities of the controller to navigate the aircraft in smaller space than with conventional wings. Okay? So this links very difficult physical properties, where the material is design variable, with something like as the guidance control of the aircraft. Also, there are no pneumatic controllers. Everything is electrical, okay, in this aircraft. That makes the vehicle management system a monster, right? The thing that controls the wings, the controls your air conditioning or your seat, the one that controls your power for your computer, the one that controls the engine, and so on and so forth. So in a challenge problem that we work together with Berkeley and Caltech and United Technologies, we looked at the vehicle management system, the electric part of it, for an aircraft like this. Okay? And that's courtesy of you at UTRC. So you have a very large network, miles of cables, generators, and various loads. So this is actually a more difficult problem than the power grid problem, believe it or not. I have variable loads. I have various loads here that I cannot afford to lose because they run the engines. I have many other critical things. So this has safety, criticality, size, heterogeneity. And this is a picture of it. I purposely picked that one because I do intend to make it easy. Right? This is very complex. Right? So we picked these parts to look at, subgroups of our group, not just Maryland. I mentioned Caltech, Berkeley, ourselves, and UTRC, to look at pieces of that and try to put them together. And we went through at least two of the pieces I mentioned, and there's the development of the third. Creating an integrated hub that I will describe next, linking to trade-off analysis tools, and then trying to understand how to deal with the requirements. Okay, this is what's called a one-line diagram of a simpler system, not the one we studied. So what you're going to see here, if you look at it, there are generators, there are HVAC systems, there are all kinds of things that they consume energy. You have variable loads, and so on and so forth. Okay, so in the integrated hub, which is primarily the work of Leonard Penga and Dimitris Sidiropoulos, look at this. We had SysML, and then we linked it to various kinds of tools for like Modelica or MATLAB to create models of these components, and the trade-off tool. Okay, and the meta-modeling tool that we used initially was this generic modeling environment that came from Vanderbilt, which is a bond graph. Bond graphs were used by mechanical engineers, and we use it here. And we create various Modelica profiles to link to these tools, and we were able to create diagrams that represent in SysML or in the various languages that we use of the components here: a generator, right, a rectifier, a load, and then it was done hierarchically by this group of people. Okay, so this is a big picture of it. So you can see you have this SysML in the model we uses a block diagram, and then you have various domain-specific languages that they link to various parts of the system, right? And there are various incarnations of this model, like what Berkeley did and what we did and what Caltech did was different to demonstrate that, for instance, it's a framework and you don't have to use just the particular tools we used. And the steps you go through are these. You basically, you create a meta model, okay, and then if you want to link, for instance, Modelica to SysML, which has been now done officially through OMG, right, and there is a profile and so on and so forth, you can create this integration of SysML with Modelica, and then we use this meta modeling that came from, these acronyms come from this IMOFLON meta modeling language we got from Darmstadt, from Germany, that is open source. And we linked it, and then we were able to link this to this modeling and create these meta models that we needed for this system. And now you have a system where you can actually simulate it and see what it's going to do in terms of consumption of electricity versus various time-varying loads. Okay. Now I'm going to go very quickly through some diagrams just to show you that this is real and it's not dreaming. So we do create profiles and block diagrams, and I don't expect you to read. It's just that these are consistent with the SysML framework and the language framework like Modelica. And we go through and we create the meta models, okay, that Modelica links to, and then SysML and Modelica can go back and forth, and you can link then trade-off analysis tools. This is the simplest one that I can show you, where you have an armature, a rectifier, and so on and so forth. You build models for each of these components, and you go up to the hierarchy, as I was showing in the hierarchical diagram. They all have parameters and so on and so forth. This is related to the previous simple slide. These are blocks, okay? And this is basically in a Modelica environment of the input model and the various constraints. And you can relate this to the domain-specific language, and at the same time, SysML captures this, and the meta model captures this. Okay. And you can make, as you can see, many complexities which are usable. You can take them and use them something else and so on and so forth, because there are design patterns behind here. And these are diagrams which we use to capture the requirements, okay, and put them into the traditional thing where you put the design variables here and so on and so forth. Okay. And the behavior and the structure and all that. Okay. So, and there are papers on that, and we have it in the university, and come and look at it, and there are a few other examples of this. So this is trying to address one of the challenges. How do I build an integrated modeling hub, which has, again, something like a block diagram with languages, which is like SysML, enhanced by semantics, and linked to various kinds of models of the physical world or the cyber world in a hierarchical way. The next challenge was, how the heck am I going to link to that, to a trade-off analysis tool, so I can actually do design space exploration? And there are two challenges here. First is this, that you have multiple objectives and multi-metrics. So I have to use a combination of things like CPLEX and things like ELOG. You can use your own. And various kinds of algorithms that they do trade-off analysis in terms of Pareto and multi-criteria optimization, okay, and constraint-based reasoning and so on and so forth. CPLEX and ELOG are completely integrated. So you can actually move from a constraint-based thinking on requirements to a metrics and back and forth. There are many others that you can do. And this shows you this integration that you need to have. ELOG is a rule-based system, and you integrate it between linear and mixed integer programming and the constraint-based reasoning framework that we have. Okay. So now I'll show you how we did this and how we use it for the vehicle management system, and for another example that many of you may be interested, which has to do with smart grids and microgrids. Okay, so here the interest is I have time-varying loads and I have time-varying generation, and I'm trying to schedule the generation of load so I can meet it. And that's, again, a multi-criteria optimization problem with many constraints, but in a different domain. I'll show you the same tool used for the vehicle management system and the microgrid. Okay, so and this is how it goes. All right, so you have, if you like, a magic draw, which is like a SysML tool, right? I can use IBM's, I can use Magic Draws, I use any other company's SysML. And I can have here our own optimization tool. I'll tell you why we use our own, because we want to capture functional constraints, which nobody else can do, meaning I want to be able to capture constraints of a type, my function has to be between two functions, which are essentially infinite constraints if you try to translate them to traditional constraints, because you have to take samples at various times to represent that. We have a tool that we developed for many years in Maryland. It's called Console OptCAD that can do that. CPLEX cannot do that. Again, I'm not trying to advertise our tool. Our tool is open. I'm trying to tell you what you need, because some of the constraints you have in systems are not just involving the variables at one only instance. You have sets of variables. And then what we go through here is, okay, we create a set of adapters, so we can actually go to the integration framework using Enterprise Architect, the Imoflon, and the Eclipse environment to be able to link the models with SysML and the trade-off tool by using profiles. This was done actually, believe it or not, so to show you that this is not so difficult that nobody can do it, by a master's student in his master's thesis. Okay? And the tool is behind, and we can do similar things with other tools that you like. And when I say a functional constraint, if this is your production, the green is the curve that you see here, which is a performance curve, should be between these two functions. And it definitely should not go below the red, because that's a no-no. It's a hard constraint. Okay. And in this Console OptCAD tool that we have developed, you can specify good and bad values, meaning the tolerances of the constraints. And there's a graphical tool that goes with it that shows you by these arrows how close you are to violating your constraints, which represent your specification, how close you are to satisfy them. It shows you which ones you violate the most. So the point is that you can interact with these tools at runtime to direct it to address certain specifications that they are the most violated, and so on and so forth. So you have a best chance for the next iteration to have a better system that satisfies more of the specifications, and so on and so forth. So it's a very interactive tool. And the meta-modeling layer, where we use the meta-models and transformation rules in Imoflon, this program that we use from TU Darmstadt, they use this metaphor of story diagrams, which are shown here, to describe the various kinds of behaviors and the meta models that you use. And they use Eclipse, which is popular, and so on and so forth. So we link this by constructing, in a profile of console OptCAD in the Magic Draw environment. This links now the trade-off analysis, with SysML. SysML was linked to the modeling via the parametric diagram of SysML. Right? The reason we introduced, or I didn't, the people that introduced parametric diagrams SysML was precisely you can actually capture parameters and be able to do design space exploration. So this fits that idea. And in this integration, these are details perhaps, but these tool adapters that they are like interfaces between Magic Draw and the modeling things or CAD tool, they also can be thought of as middleware that I have that allows me to call the various things without violating any of the rules of the programs I'm using. Okay. So this is the linkage to the parametric diagram of SysML for various of the parameters that I introduced in the various components of the system. And that's how the loop goes, right? So I have the models in SysML. I initiate the transformation. I link to console of CAD, and I get the output, and keep going. Okay? So I model. I go through the meta models, link them, link to the trade-off analysis tool, and I see the results here, and I keep iterating until this is how I do design space exploration, until I get a chart here or a graph that I'm happy that my specifications are satisfied. And this can be done in any of the domains that we work in engineering. It doesn't have to be electrical or mechanical or chemical and so on and so forth. The key is to be able to translate your requirements and specifications to mathematics of inequalities, rules, and metrics, so that you can actually play with them. And to make it more precise, I don't want to bore you with equations, but in the microgrid problem, we had an operational cost. We tell you how much power you have and various parameters, minimize the fuel cost, minimize the emissions. The parameters were the power output of the engine, the time of operation, the efficiency. So I'm giving you these numbers to show you that what I mean by formulas, right? You take these language constraints, and you translate them to some quantitative thing that represents your cost. And you have several. And then you want to meet electricity demand. It has to be more than this demand. So this function can be from data or can be the one you want to use. And you have constraints. And notice that I'm giving you constraints here which are difficult. I'm telling you when the machine has to be on or off. Right? These are not very easy constraints to handle. And I also give you constraints where once I turn it off, because there are costs in turning off and down, it has to stay on. Or when it has to be off, I cannot turn it on again. So this is a difficult problem because it has these functional constraints. A function has to be between two functions, and it has hard constraints and soft constraints, which is the framework we use. And it's not small. It has the 15 design variables, 10 constraints, and 3 objective functions. Of course, the software we're using is scalable. And as long as you do it hierarchically, you can do very large problems. And so is Cplex and ELOG, and so are several others. So here's what happens. You run an iteration, and you get the red dot here, which says that a hard constraint is not satisfied. These arrows, this we call the comb, because it resembles a comb. You have to be between the good and bad values for the various specifications. And you see here that this is not satisfied. So the first thing that this program is going to try to do, it uses an algorithm which is a feasible quadratic programming, which means after a few iterations, every solution that you get, you can use it as a design because it's feasible, meaning it satisfies, right, the constraints and metrics that you want. And that's beautiful because you don't have to project to your, if you are into this part of mathematics or analytics. So then the user here does not interact with the optimization process until all hard constraints are satisfied. So you saw that, you say, run it again. So that was at 25 iterations, you don't see any of this, right? The hard constraints are satisfied. Hard constraints means the aircraft has to be stable. The heat has to be below 10 degrees. I cannot violate it at all. Soft constraints means, I can violate a little bit. I have more tolerance. All the objectives here are within limits, and now I have the functional constraint, which is not very good. So in this case, you have a solvable problem, It's feasible. Once you get a feasible solution, because of the feasible sequential catalytic programming algorithm we use here, there are many others that have this property, anything you do after that is going to remain feasible. What you don't like here is you generate too much energy. You look at it, and you say, okay, I'm feasible, but I'm generating too much energy. Can I do better? And then you interact with it, and you change the cost. And you can see now you can produce less energy, and you still are feasible. How many times?
Can you weight those objectives? So
Yes.
one is more important than the other, or the other is less
You can, but I wouldn't do that. Because unless you have a wise guy that's going to give you the weights that you trust, I won't do that. Because the theory is that if I do trade-off analysis, as you know, and I get the Pareto curve, these weights are the perpendicular to the tangent. So if you're going to do that, do it at least for a range of weights so that you understand the sensitivities. Don't do it just by a single weight. What we advocate is if you can do trade-off analysis, please do it. Don't mix the metrics and so on and so forth. But they're equivalent, okay, mathematically. All right, so for the VMS formulation problem, so that was one problem, which was the microgrid. Now I go back to the VMS. I want to maximize the serving of the shed double loads. Shed double loads are the ones you can turn off. Well, if you get too hot in your seat and I have trouble in the aircraft, I'm going to turn your air conditioning down. I mean, okay, that's fine. I cannot turn the engine down. So there are shed double loads and non-shed double loads. I have to minimize the fuel cost. I have to minimize the procurement cost. So there are similar kinds of problems with many constraints and many variables in the VMS program, the vehicle management system, and we use it the same way. Okay, so you basically see again, I do through the first iteration to the second iteration, you interact with it until all the things come between the good and bad values, and you have a feasible design. Okay, so in this brief presentation, I'll show you how a framework to tackle two major problems in system engineering. One is integrated hub. The other is this trade-off analysis tool. Okay. Then there's a whole bunch of slides which I will just pick a few to show you how many more things you can do with these techniques and how many more work we have to do collectively in an open environment to make this really into what it's supposed to be. So the work of Brian, who's over there, is trying to apply these techniques to wireless sensor networks, develop model-based system engineering for wireless sensor networks. If you want to do a sensor network for defense or for the building and so on and so forth, right now everybody starts from scratch, right? So what he's done is he has a system framework. He creates libraries of components, software, hardware, heterogeneous sensors, and puts them into the modeling part, right? All these things, he's right there. You can talk to him. And then you can do trade-off analysis using similar techniques as we have here. And the example that is in these slides, by the way, I have no problem to give them to you and you can post them, since I'm trying to get people to work with us. You have model libraries, and you have libraries of the protocols, of how the wireless sensor networks communicate with each other. You have libraries for the different types of sensors, their capabilities, and so on and so forth. And this is a simple example of a sensor network for a building and a heating. Okay, forgive us for the pedantic, very simple example, but that's to illustrate that you can actually run all that, and you can do various kinds of simulation scenarios and figure out what happens for the energy and consumption and so on and so forth. Okay, so you can get things like, you know, what is the data center temperature, the living room temperature, and total electricity cost. The deal over there was that whether you want to have a communication between the two rooms to actually have a better temperature balancing and so on and so forth. Techniques like that you can use for something which is very important today to try to understand what happens in the rearrangements of computers and other things in data centers to save energy. Or if you want, you have several data centers, and you can try to find out how I can move the data around to at the same time do combine routing and heat control and other things in data center, which is a hot subject right now. Okay, a few words, and I finish. If I can finish in about 5 minutes, I will. So this is all fine, but there's another problem. Okay, when you try to do design space exploration, you get into this problem. Okay, you have to start asking questions: which variables I'm going to change or why? Okay, and then you have to try to figure out how do I look at the system or the block diagram from the perspective of these variables I'm trying to change. And that means I have to create a new decomposition of the system based on the variables that I care about, and the ones that I don't care about, I aggregate, I put them aside. That's a difficult problem because it has to do with rearranging the block diagram in a way that is A, searchable with a small complexity, okay, and gives you the result that you want, right? So you can trade off. So with Sean Yang, who used to be a student of mine, then he went to BAE and came back and worked with us for a couple of years. Now he's with Google in New York. And we developed a system like this, okay, which uses some techniques from trees and decomposition and so on and so forth, and things from computer science, right? Satisfiability theorems, searching, logical trees, and so on and so forth. And it has to do with the following idea. I'll try to skip some things. It's a divide and conquer. I want to be able to take these variables and think of them as queries, and then divide the system in a hierarchy of components that they are affected by these variables, and then search it quickly without going through exhausting search. All right? And I'll show you in a simple example, which has to do with medical applications, that this reduces the order of number of searches you want to do by 2 or 3 orders of magnitude. When you're trying to, because when you try to do design exploration, you have many variables and many constraints, you come to this question, okay, what do I change and why and how so that the next one I'm better? And you cannot do these questions by complete search. You have to be very effective, efficient in doing it. All right, so I won't tell you the mathematics, but what it does is you can think of the system as a graph of components connected by links, which characterize influences, and then these nodes, they have variables associated with them. Some graphs, those that are chordal, they have very low complexity when you do these queries. Others don't. Fine, that's not bad because you can make them chordal. And by making them chordal, it means you collapse variables to one. So the practical implementation is I do a search now on both those variables, not in one. And that reduces the complexity, and you can do it not in exponential time like it is if you don't do that, but in linear time. Okay, and that's the key idea here comes from computer science is that the complexity is exponential in tree width and linear in the width, but you can actually, by doing the composition block diagram to look like a chordal one, you can make it linear. Okay, so there is in the slides, there is an example of how you do that for the design of a quadrotor and what it means to link quadrotor. You know all of the quadrotors, right? The ones with the 4 things on the thing. Right? So here you can see various variables you have, weight and so on and so forth. And by making the query chordal in terms of trying to find out how you're going to search for design space exploration, it makes it very fast. Okay? And that requires these so-called fill-ins, right? Which basically you link variables and you think of them together. Okay, so let me finish with this, with a putting in front of you. So you see, it's like taking the block diagram with the various variables and looking at it from a different perspective so that you can actually reduce the block diagrams vis-a-vis the variables that you care about. This is how we view these queries. And there are papers on this that are published on my webpage, and you can look at them. Now, what do you do if the system that you're trying to do this has behavior, is dynamic? And the example I'll give you may surprise you. It's come from a work we had done for trying to apply system engineering principles to manage intensive care units. And we did this because many people said this is very important. Companies were involved. Even the president of the Institute of Medicine has come to Maryland and said we need more system engineering thinking in medicine. We're never going to conquer the quality and cost of medicine unless we start thinking like this. And the question here is that you have a lot of the virus. If you go to an ITU, right, the intensive care unit, they put various things to follow you, and they give alarms. And one has to correlate the alarms before some nurse comes to you, right? Because most of these alarms, they don't need a human or a doctor to come and see you because they are not serious enough. So this is not done. So this creates a lot of time wasted and a lot of cost associated with that. So what you have to do here is you have to develop models of the processes of the patients that they go through, right, and what is done. So let me paraphrase and use a language that is very offensive to doctors, okay? But I'm a scientist, I don't care. So you think of the patients as the product of the intensive care unit, and you think of the various stages that you go through a therapy as the processes. The analogy is with manufacturing, right? So in integrated product process design, we have done complicated things like that. The difficulty here is that each patient is different than the other, so they are not repeatable like in manufacturing. If I make a an RF module for radar, I have to make them all the same. The patients are each the case. So the complexity is huge, and it's here that we use this reduction of the complexity in the queries to go from millions of searches to a few hundred, and be able to understand what do you do to reduce the cost in an intensive care unit. This was the first study of its kind that we did. Okay, but we use this framework, right? We use the framework. And the models that we use are here. They were models that have to do with patients, and some of these analysis models were cost analysis models. Okay, I repeat the picture. Okay, and we use statistical models that go by the name of Markov chains. They have a lot of states, and when you try to do the searches, you go into the millions. And by this reduction method, we were able to get it down. All right, so let me finish. This time, you see, you would have gone up here, and we went down there for the searches to be able to find the trade-off analysis between various things we propose on the process and so on and so forth. So now, some areas we work. I won't comment it. We work on trying to componentize protocols for wireless networks by this method, thinking of the wireless network as a system with various components, including breaking the routing protocols to pieces and so on and so forth. We had success to that, even with beating RFCs. Okay, we're looking at security as a systems problem in an area that's called composable security, especially for wireless. Composable security says, I have this piece of software, this piece of software, this piece of hardware. Somebody verified to me that this has high security. I put them together. How secure is the system? What do you think? There are theorems that tell you it's not secure at all, unless if you do something like a third-party trust, or if you have some of the nodes that you have that they have higher hardware security and so on and so forth. So this is a very important topic for the wireless world we live in. We use the same techniques. We're working on FAA, next generation in this area. We're working on energy efficient buildings. This effort is headed by Professor Austin in thinking of them in systems engineering. We're doing something very, very interesting. We looked at how you make MEMS and nanos today, and this is how we used to do VLSI 30 years ago. You have different parts of software that they create files, and you read the files and you interact with them. So this is an area where we're trying with various people that we have in the institute and other parts of the country in the microsystems world to create a systems engineering framework for designing these things like you do VLSI. But MEMS are not VLSI. They have different physics, okay, and nano and all that stuff. And then we're looking at automotive with General Motors. This is all work I did with when Northrop Grumman used to be called Westinghouse. This was for designing RF modules, where I learned some of these things, and then we mathematized them. And this is a version of this tool that handles logical variables. This is, again, console of CAD, but now the variables are logical. We have both worlds on this. Same idea. We're now moving to robotics, where we're going to make the material as a design variable. So I want to make a robotic arm, or I want to make a walk that walks. What material should I put in the legs, and why? Right? Not take it for granted. We look at swarms, or if you like, collaborative robotics from a system engineering perspective. Yu-Chen Zhu, who is not here, is a student of mine who works on this, and he is working on this. All right, in the lab we have. We're working on health IT, and we're working on this area, which is huge, and it's the one that mostly needs engineering thinking in systems biology, except that you don't have enough models. But we did work with a student of mine on trying to develop models for Alzheimer's disease. She's now in a medical school, using these techniques, but now we're dealing with biology and chemistry and things like that. We found out that the beginning of Alzheimer's is not what everybody believed. It starts when there is an inflammation in your brain many years ago, and then and this was verified later by people at Duke. By the time you see plaques, it's too late. We build dynamical system models of the various networks that interact in your brain, and by exercising them, we were able to find out early instances of abnormality, and then verify those by mice. Okay, and we are continuing these works. He's now in the Penn State Medical School. And the last thing I want to mention to you is we're working on synthetic labs on a chip. This was an idea that came from a professor at Cornell, where the idea was to try to create silicon models of human parts on silicon. And then we thought, if you're going to do that, let's actually have 3 parts on a chip. One is software, one is hardware, silicon, and the other is in vivo. And why? Because you want to test side effects of drugs for a particular disease. We've talked to pharmaceutical companies, and they told us that what they want is a way to create customizable drugs, where the customization comes, if I make drug A, I will now make 5 categories of the drug A, tuned to the genomes of humans as per their side effects. They claim that this can reduce these costs by 5-fold. Currently, the average cost for a drug is about 10, 12 years and about $1 billion. In the Wyss Institute at Harvard, we started 2 years ago, they have the ability now to create liver cells or pieces of liver on this lab on a chip, but not for this purpose. So we're trying to create some sort of a consortium to work along this direction for pharmaceuticals. Okay, that's the research. Now, we teach this in this program we have in Maryland for system engineering. These courses 621, 622, 623 are focused on these quantitative models. If I'm not asking you to come and take the courses, but try to work with our students as interns and others, and try to work with us as we develop this program. And last 2 years, we did a rather daring experiment. We tried to introduce some of these ideas to undergraduates in a class that was first funded by the Department of Defense 2 years ago to try to introduce this on a hands-on experience. And you can help there by being a mentor to these students and work with us on projects that you want. So these are very bright students. We select them very carefully. They work on projects ranging from smart tires to minuscule nuclear reactors, using these ideas in an introductory fashion, learning how to use industrial strength tools, but on a small problem, so that when they get out, they won't be surprised about the tools. They may be surprised by the size of the problem, but not by the tools. And we're working on that with companies and labs to try to give them this experience and try to encourage them to at least get a master's in system engineering and not try to get out in the world with just a bachelor's. So if you're interested in working with us in any of these, either on research or in students, you can contact me, or you contact Steve Sutton, who is here somewhere, right over there. He's the director of our system engineering program, and you know him. I'm a member of INCOSE, as I said, since the beginning. And thank you very much for your attention. And I can take questions if you want any.
Any questions?
Yeah.
Can you compare the complexity of the problems you're tackling with something like, say, protein folding, to give us an idea of the complexity that you can handle?
I can compare with protein folding if you give me an algorithm that you trust that it does understand protein folding, all right? So if there are some simple proteins, I can do it, but in general, I can't. I mean, the problem with biology is there is very little known for models and quantitative algorithms. So I know I'm not answering your question, but that's the best I can. If you give me something that does protein folding for a particular protein, then I can put into this mathematics, and I can try to, especially the one with the decomposition, and try to understand the complexity that it has. Yep.
This is more in the form of a comment than a question. When you had the slide of the Dreamliner up there, you made the observation that there are a number of people who think that electricity is a higher form of energy and is likely to be the predominant form of energy in the future. And I, for one, used to be a firm believer in that. And I set out to prove it by calculating how much it costs to transmit energy in various forms. To my absolute amazement, I found out that it is much cheaper to ship energy in the form of chemical energy in pipes than it is in the form of watts of electricity. Factor of 3 or more for gases, even more for liquids. And that set me back on my heels. My perception of where we're going is not
That's true. That's true. But remember, here we're talking about a platform, meaning a car. So if you are in a car, you're not going to send energy in chemical form from one chip to another. If you are in the aircraft, you're not going to do that either. So I guess there are 2 parameters of electricity that are useful. You can manipulate it and change it very easily in this sort of networks that you have in a car or in a vehicle or in a home. As far as the grid issue, I'm with you. That's perfectly okay. As a matter of fact, why many of the smart grid applications do not go very well is because they forget in the system studies they do to account for the cost of transmitting energy. Because all these renewables, they are not going to be generated where you have consumption. Right? So the lesson we learned from Germany was that, let's say you take wind power or solar or photovoltaic, the principle is you generate it and you consume it locally as much as you can to avoid to build a transmission system which is very expensive. If you include in the system cost analysis the transmission, many of the proposals that have been made, they go the other way. Exactly the point you're making, okay? It's not, so yes, for the grid, you're absolutely right. For these things, people are advocating that the all-electric platform, meaning all-electric, and for the house, I debate it. Because there are ways to save energy in the house by putting plants on the roof. We have students that are working on that. After all, Maryland won the solar decathlon last year, right? And one of the students is in our team trying to take some of the ideas in the watershed project that they did, which won the first prize in the worldwide solar decathlon. And using these techniques, you can save energy by putting plants on the roof or changing the walls and other things. This is nothing to do with electricity. So it's more appropriate maybe for the car, the all-electric car, or the all-electric aircraft and things like that. You remember the aircraft that had solar cells or photovoltaic and flew from one seat to the other in Europe and things like that. So people have interesting ideas along these things. Yep. Yeah.
Yes, I have quite a lot of experience in aircraft design using the old methods. And I'm having a little problem understanding where the role of innovation would come into this process. I see the lessons learned, where you can go and take existing designs and bring them up to date, and I accept that. But, you know, a lot of our great, things that were added to the technology, if you will, were innovative. They were created by the human mind.
Always.
Okay, and I don't understand how we get that into this law.
Okay,
I
see,
don't know.
very good question.
Engineer is, as much as I respect this profession, I don't think that we have a lot of aerodynamicists. I don't think we have a lot of thermodynamicists. And I don't think that the innovation will come from this community. So
You don't.
how do we get that in there?
Okay, I'll tell you. Let me go back to my to this diagram, if you like. Okay, so the system engineer is like a composer. You have an orchestra. You need the expert flutist. You need the expert pianist. You're not going to replace those. You're not going to replace your expert fluid dynamicist and so on and so forth. What the system engineer will give you is the conductor. It will make them communicate with each other so I can understand that the overall system is going to be better, not just one component being better and the other not being better. And to make the point, in the Dreamliner, the question was, okay, so I'll do the composite wing. Initially, they did it for various kinds of different reasons. And then they tried to understand what is the effect of a composite wing versus a traditional wing in terms of maneuverability, and whether they could actually link this to the requirements of FAA for next generation and so on and so forth. And that to me was, I know the person who did the study, it was an amazing study. But again, you're absolutely right. The system engineer will not give you this kind of innovation. The innovation you should expect from a system engineer is the following. Could you give me a component as such? Because if you would, here's what I could do. So it's like the periodic table in chemistry, right? That you can say, gee, I mean, if I had this component, look what I could have done. So the system engineer can actually do what we call component synthesis, take the components or the platform, and see how you combine them to make a higher performance or a higher reliability and higher safety system. And the innovation there is in the framework and the tools and the methods. But you're not going to do the same kind of innovation that the experts you have in your team will do. This is a different dimension. However, if the system engineer will give you tools that the experts can communicate with each other, then my belief is that then the innovations that they individually will do, it will become faster and more effective and easier to be implemented into systems. So this is not replacing the in-depth engineers you need. It's just trying to make them, like a conductor will make the various experts play together than the solo player.
I great danger in missing innovation. Most people I see developing systems, I've been involved in developing systems, mechanical systems, that use electrical and computer interfaces that we're so good at analyzing. They don't have a lot of patience. The design has to move on. So there's nothing in the previous invention bin. They're not happy.
Well, I kind of disagree as far as whether if you had these tools and they become like MATLAB is today, like 10 years from now, this is on everybody's desktop and it helps the engineers within a company or other to converse in various options this way, I think the innovation rate is going to be more important and faster.
Yes, but I'm trying to suggest that we don't have an easy path. I'm not saying the path doesn't exist.
The path. The reason I put this slide up because none of the tools individually or the theory that goes behind is easy, and putting this together is not a trivial task. But I think collectively, people started understanding that collectively they can do it. So the innovation here, if you allow me the expression, is a little bit invisible because it's a framework that we have and we use it. And out of that comes a new airplane or a new component in an airplane and all that stuff. It's not the same as the engineer you mentioned that he invented the new mechanical gadget that everybody can understand and see, because this is going to be hidden here.
I understand, but the equations of motion of an aircraft are not easily displayed in this kind of.
They are in the behavior.
I don't see a differential equation.
Well, but that's what I mean.
And I'm not saying they can't be expressed in these things.
No. What is your name?
The system engineers may not be able to effectively use them.
No, they will, because you see the next diagram here shows you exactly that, right? When we do this, right, the differential equations can be here, they can be here, they can be here, they can be here.
I don't question they can be there, but are they?
And the folks that they work on the projects I described, okay, when they use, for instance, Modelica or Dimola or MATLAB, there were differential equations there. And they were difference equations, and they were logical rules. And they were combined to try to interface with the block diagrams that come from SysML.
And I'm very concerned about changing that to a digital format.
So
I think that something may.
the problem we have in engineering education, and there are very few universities that have done it well, is to teach engineers from the undergraduate years, I believe now, to think systems, even if they are not going to be systems engineers, to think that, hey, I'm going to be an expert hydraulic engineer, to use your example, but I have to work with electrical engineering folks and understand the difficulty of that. And understand it's like conversing in the United Nations, right? If I go through a translator all the time, forget it. If I know a little bit, this is not perhaps a good example, if I know how to converse with you, if I have the tools that allow me to see what we are building together through my lenses and you through your lenses, I think we're going to do a lot better job together. I think the era of the expert engineer that sat in his lab and came up with one innovation or two in his lifetime, and that's how he became famous, I think is gone. The expert engineer, he will be a lot better expert engineer in his specialty if he works and understands how to work within a system.
Okay, on that note, I want to thank you, Doctor. And I want to just, before we do our book drawing, because we are running a little bit
Thank
over
you.
here, does everybody have a ticket or a makeshift ticket tonight? It's a little piece of paper with a number on it.
Artfully constructed.
Artfully constructed. Thank you, Mark. And thank you, Harry, for the great idea.
Do you have a card?
So tonight's book is the Practical Guide to SysML, the System Modeling Language from Sanford Friedenthal, Alan Moore, and Rick Steiner.
Yep.
It's a second edition. And we're going to need a book report. And as usual, our speaker picks the drawing.
I'm not going to look.
If Steve Sutton wins this book,
Yeah,
this
it
thing
is.
might be fixed. Number 8. Number 8? Who has number 8? Dig deep, folks. Look, he teased us. He got up and left. Thought he was coming down for the book. Number 8? Nobody has number 8. Okay, one more.
Oh, I spoke too long. That's
Yeah, right.
okay.
Number
Th-
36. 36? 86.
Okay.
Ron, very good.
He used to be a student of mine.
Couldn't wait to... We were talking
It's
earlier.
true that he used
Wait,
to be a student of
Come on
mine.
up.
But it's good for him to get the book, yeah. Okay. Yeah. Yeah. Here. Yeah. That's a reunion picture of after 20 years, right?
Yes.
Thank you.
Congratulations. So, Doctor, we have a couple tokens of our appreciation here tonight for you coming out and sharing your knowledge with us. Our first one is our Chesapeake chapter coin,
Thank you. Thank you.
and then also our Chesapeake chapter coffee mug, which is a little comical there. It's not a
Great.
mug, it's a caffeine delivery system.
I'm a heavy caffeine drinker, so this is useful. Thank you.
Perfect. And then a certificate of appreciation, sir. We just
Thank you
shower
very
our
much.
speakers with gifts. So
Thank
this
you very
is a
much.
Plug for our speakers if you want to come on out.
Thank you. So I have a practical question. How does one get more involved in the chapter activities?
Just,
Since I started by saying, well, let's make 1,000 members or make this room full every time. So how do we get involved?
we can speak to any of our board members or any of our members here at the dinner. We can get you involved.
Because after all, we're not very
Dr.
far.
Don York is our president,
Okay.
current.
Well, our group, our students, our faculty, how to get, I mean, those that they are interested in this subject, yeah. Me personally, and,
He's talking to our liaison,
okay.
the ISR, so he's a good point of contact with them anyway. And you can, our program director, if you have a program or something of interest that you want to present, go to the program director, it's a board member, and we can,
I just have one suggestion first. Before you take the time to
Yeah.
give yourself to the chapter, take some time to
Ah,
handle that desktop.
See,
That's-
this is, does anybody know what the answer, what my answer is going to be? You're excused, you cannot say anything. This is my security. Right?
Very good.
If you're going to find a file, go find it. I can.
Thanks again for coming out tonight. Appreciate it, everyone.